In the double slit experiment, if you know which slit the electron go through, this happens. The interference pattern vanishes. That's what we've been taught, but that's not true. But what does actually happen? And why do we keep telling this lie? Hi, I'm a physicist, and this is arguably the biggest lie we teach about the double slit experiment. I've been told that you have this weird wave pattern, but then your measurement destroys it, and you're left with two single slit blobs. And I thought that has in it the heart of quantum mechanics, that it contains the only mystery. But if you close one slit, you don't just see a single blob. What do you actually see? You see this. There is some kind of pattern. This is real footage of an actual double slit experiment using electrons, and we're gonna see more of this later. Importantly, it's not a single blob. Something's wrong with our story. But what? What is it? Why do we see this, and did Feynman lie to us? To understand the actual double slit experiment, we first have to look at the way it's usually taught. And in the end, we'll talk about why it's usually taught that way. Like most of you, I've been taught the double slit experiment the way it was presented in the Feynman lectures. If you send a wave through two slits, the two resulting waves overlap and form a new wave pattern. If two waves meet and their peaks align, they form an even bigger wave. But if a peak meets a throw, they perfectly cancel each other out. That's what we call interference. Waves overlapping and forming a new wave pattern, which we then call interference pattern. Importantly, that's not what you get when you send out tiny round bullets. They just give you two blobs. Now, the double slit experiment wants to tell us two important things. First, electrons are not tiny round bullets. But second, as soon as you measure them, they look like this. If you do the experiment with electrons, one electron will give you one dot. The measurement, the interaction of the electron with the screen, makes it particle-like. We can stack the dots that landed in the same region on top of each other and get this wave shape. So, if you look at many electrons, you clearly see that they did not behave like particles before arriving at the screen. You don't get two blobs. You get an interference pattern, just like with waves. So, electrons can't be particles like dust particles. They are quantum things, and maybe we should call them differently. Wave behavior like interference is why we describe electrons with a wave function, which is, by the way, not an actual physical wave. The math of quantum mechanics does not say that electrons are physical waves. That's something I explained in this video. But importantly, we see an interference pattern in the distribution of the electrons. The wave function interferes with itself, kinda like two water waves interfere. The fact that this can happen is a fundamental feature of quantum mechanics. The wave function can be in a superposition. So far, the standard explanation is good. So what comes next? Now the Feynman lecture tells us what supposedly happens if you measure which slit the electrons go through. You could block the two slits one at a time, or you could watch the electrons with the help of a light source. The light would scatter off the electrons and you would see a flash in the region of the slit. If an electron passes through hole 1, we would expect to see a flash from the upper hole, and the other way round. Here's what we see. A flash of light either near hole 1 or near hole 2. From this observation, we conclude that when we look at the electrons, we find that the electrons go either through one hole or the other. So far, so good. But we're getting close to the misleading part, the myth we all fell for. Feynman says we will count the electrons and also keep track of which hole they went through. From the numbers we get the probabilities that an electron will arrive via hole 1 or hole 2. The curves are similar to what we got by blocking hole 1 or 2. So far still good, but now comes the shape of the resulting curve. This shape is the myth we all fell for. There is not any complicated business like going through both holes. The electrons come through just as we would expect them to. Each of these probability curves supposedly corresponds to a single blob. That's what Feynman says you would see on the screen. No complicated business. The electrons come through just as we would expect them to. But you already know that blocking one slit you actually see this. There is some complicated business. It's not what I would naively expect. So, let's take a look at the actual double slit experiment. In this paper, these people did the experiment Feynman presented as a thought experiment. Spoiler alert, I will come back to that. For now, let's just say doing this experiment with electrons is extremely difficult. Why? Well, because an electron, or rather a wave function describing electrons, has a tiny wavelength. So to see any wave behavior, everything must be tiny as well. For example, the distance between the slits. It cannot be much larger than the wavelength. Otherwise, there would be no interference. Here, the slits were 50 nanometers wide, 4 micrometers tall, and separated by 280 nanometers. To reveal different patterns on the screen, they blocked different parts of the slits using a mask placed behind the slits. They moved the mask from one side to the other. And that's what they got. This tells us the position of the mask. At first, it blocks both slits. As it moves, slit 1 becomes partially, then fully open. This is the single slit interference pattern. Then, more electrons can go through both slits, and when the mask is centered, you see the double slit interference pattern. The mask moves on and the reverse happens. The double slit pattern changes back to a single slit pattern. This is so cool, right? And here, that's how the interference pattern of the double slit builds up, when there's no mask. Before we talk about this, I should mention that what you see are not directly the electrons. These physicists used their method to make them visible to us. As I said, we're dealing with tiny wavelengths, so the patterns are too small to see. So they kinda use electric fields to somehow zoom in. I don't really know how it works. If you do, please let us know. Furthermore, a single electron is too faint to detect on its own, so they let it trigger a chain reaction, multiplying that one electron into a burst of electrons. This then leads to a flash of light, and that's what gets recorded. To get these images, they then added and normalized multiple recordings. And to get this building up pattern, they used what they call a plop detection scheme. I don't know what it is, but what a fantastic name! If you think this video is fantastic, please leave me a like, it helps a lot. Thank you. So, this is the pattern you get for the double slit, and this is the one for the single slit. You get a big blob in the middle, but you also get smaller blobs on the sides. And maybe you already guessed it by now. This is an interference pattern as well. If you do the experiment with a laser, you see it clearly. A beautiful interference pattern, not a plop. But that's not all. Actually, the double slit interference pattern kinda contains the single slit pattern. But let's first try to understand why we get a single slit interference pattern. Interference results from overlapping waves. So you need more than just one wave to get interference. In the double slit experiment, there's a wave or a wave function coming out of each slit. 2 waves, interference, no problem. But if you have one slit, shouldn't you only have one wave? If the slit were infinitely small, then yes. The simplest way to picture it is like this. You have a wave from the upper edge of the slit and one from the lower edge. And now they interfere. Actually, it's a bit more complex than that. But importantly, the geometry of the slit changes the wave. Different parts of the wave arrive at the screen with different phase shifts. The distance from here to the screen is longer than the distance from here to the screen. That's why the waves arrive shifted relative to each other. At the minima, they are shifted exactly such that they cancel each other out. The pattern depends on the geometry of the slit and the light's wavelength. As the slit becomes narrower, the interference pattern spreads out more. The wider the slit's width, the more compressed the interference pattern becomes. The maxima move closer and closer together. And eventually, if the slit gets much wider than the wavelength, the maxima blur together. If you increase the wavelength, the interference pattern spreads out again. Now you might say, but this is light, what about electrons? Let's briefly talk about that, and then we'll see how the single slit and double slit pattern fit together. If you view this as the probability distribution of electrons, it works the same way. Making the slit wider has a similar effect. That's why it's so difficult to do the experiment with electrons, because the wavelength of the electron's wave function is so small. The slits must be so narrow in order to see any interference. So, this is a good mental image. But I don't know how an electron going through a single slit actually looks like. I only know how we describe it. We describe it with a wave function. And for the wave function, all this happens in a mathematical space, not in our space-time. Only the squared wave function is related to something measurable. The square of the wave function tells us how likely you are to measure an electron at a certain place. This is the probability or intensity distribution for the double slit. The red curve is the one from the single slit. So you have interference due to the single and due to this double slit. This explains why we see more distinct blobs in the double slit. If the slits become wider or the wavelength shorter, the interference pattern becomes more compressed, just as before. But now we have a new parameter, namely the distance between the two slits. As you probably expect, it doesn't change the overall shape, but only affects the double slit interference. The wider the two slits are apart, the more compressed the pattern becomes. Okay, so these are the actual patterns of the single and double slit, and not this. And this brings us to why I think the lie about the double slit is not that bad. Why do we keep telling this, if this is reality? Did Feynman lie to us? The probability curve we see in the Feynman lecture is only the central order of the actual probability curve. It's the biggest part of the curve, but it's not the whole story. It's a simplified story. A story about two waves coming from two slits instead of a wave coming from every point. Is this simplification okay or misleading? What do you think? On the one hand, it becomes easier. Understanding interference becomes easier if you're only thinking about two distinct waves. And Feynman is talking about a thought experiment. Doing a thought experiment, you usually neglect all the things you don't care about, like influences from the environment. You focus on the story you want to tell. Here it's the story that electrons are not tiny round bullets. But as soon as you measure them, they look like this. This is used to tell the story. And I can see why. But that's simply not what you actually get. So on the other hand, this might be oversimplified. You can't tell the story without this simplification, because one electron will give you one dot. So this already shows that measuring the electron makes it particle-like. Furthermore, you can get this. Measuring which slit the electron goes through, we change the wave function. The double slit pattern becomes the single slit pattern. And if you actually measure the exact position of the electrons, you do destroy all the quantumness. But it doesn't even have to be that complicated. You don't have to be the one measuring. You can use decoherence to destroy the interference pattern. If you don't do it in vacuum or you're not careful enough, you will see no interference. That's something I explained in this video. Thanks for watching. Have a wonderful day.